somewhere in the vast quiet of the universe. There is something so rare that even the cosmos seems hesitant to make it. Not a bright star or a swirling galaxy, but a phenomenon that forms only under the most fragile, unlikely conditions, so unlikely that for every trillion places it could appear, almost all of them never will. Tonight, on Fall Asleep to Astronomy, we drift closer to this quiet rarity and trace how such a delicate thing can exist at all. If this gentle kind of wondering feels right to you, a soft like and a quiet, subscribe. Help others find their way here. When you're ready, settle in. We'll drift onward together, unhurried and warm, deep beneath the quiet hills of Switzerland. In a laboratory hidden under stone and snow, scientists once held a tiny miracle. For only a few millionths of a second, about 100 atoms of antihelium shimmered into existence and then disappeared. If you could somehow gather a single gram of that ghostly substance, it would be worth more than $60 trillion. Yet it would destroy itself and anything it touched in an instant of pure light. This is the kind of rarity we are wandering through now. Materials that cannot live in our world for long, elements that burn themselves apart with their own heat, stars woven from exotic ingredients, black holes so small they could hide inside an atom and still carry the violence of a nuclear blast. You will never hold them, but you can let the thought of them rest in your mind for a while, like a strange dream that refuses to fade. At the center of all this lies a quiet, unsettling idea. Every particle that makes up your body has a shadow written into the equations of physics, for each electron helping your thoughts and heartbeat. There is a twin with the same mass and the opposite electric charge. Physicists call this family of mirror partners antimatter. When antimatter was first predicted in the year 1928, it seemed as if the mathematics had slipped into fantasy. The equations spoke of particles identical in weight to the ones we know, yet reversed in their electric nature. A few years later, high-energy particles from space revealed that this was not fantasy at all. Those hidden twins were real, drifting through our detectors like the negative of a photograph. You can picture antimatter as a perfectly reversed version of ordinary atoms, where normal matter holds negatively charged electrons around its nuclei. Antimatter carries positively charged positrons, where ordinary atoms keep positively charged protons at their core. Anti-atoms gather negatively charged antiprotons instead. The mass is the same, only the signs change. On paper, it seems like a small adjustment, but its consequences are anything but small, because when a particle of matter meets its antimatter partner, they do not simply bounce or break. They both vanish. Their entire mass turns directly into energy. In a single, clean step, no flame, no ash, no leftover embers. Chemical reactions can only unlock a tiny fraction of the energy hidden in matter. Even nuclear bombs convert less than a small share of their fuel. Matter-antimatter annihilation is perfectly efficient. Imagine, only as a gentle thought, 1 gram of antimatter meeting 1 gram of ordinary matter. The energy released would rival tens of thousands of tons of explosives. The punch of multiple atomic bombs gathered into something smaller than a sugar cube. Nature is cautious with such power. It makes antimatter only in tiny, scattered ways. Lightning storms can give birth to positrons high above thunderheads. The radiation belts around Earth trap a few wandering antiprotons, guiding them in invisible loops Far out in space, particles collide at almost light speed for an instant, create pairs of matter and antimatter that immediately destroy each other again. It is like a constant whisper of appearing and disappearing, woven into the background of the universe. Yet our best understanding of the Big Bang tells a stranger story. In the first heartbeat of the cosmos, matter and antimatter should have been created in almost perfect balance, each particle of one matched by a particle of the other. If that were exactly true, they would have erased each other completely, leaving behind only a smooth sea of energy. Instead, there was a tiny tilt for roughly every billion particles of antimatter. There seems to have been one extra particle of ordinary matter left over. Those leftovers became everything: galaxies, stars, oceans, your own hands. Physicists call this imbalance the baryon asymmetry problem. But behind the name is a simple wonder. The universe, as you know it, is made of what survived a nearly perfect mutual annihilation. Because antimatter is so rare, it is also unbelievably precious. The largest particle accelerators on Earth can create only a thin dusting of it, far less than a billionth of a gram each year. To make a full gram that way would require running the machines for longer than all of human history. And even if you could make it, you could not simply pour it into a bottle. The instant it touched the walls, it would vanish in a burst of energy. So scientists hold antimatter without touching it at all. They use carefully shaped magnetic fields like invisible hands, suspending individual antiparticles inside nearly perfect vacuums. Even then, most escape after minutes, slipping away and annihilating on the chamber walls. The idea of a solid lump of antimatter is, for now, more a story of the future than a plan. Still, within those difficult limits, something remarkable has already been done. In a European laboratory dedicated to particle physics, researchers managed to assemble complete antiatoms of helium. Ordinary helium is one of the simplest and gentlest atoms, 2 protons and 2 neutrons in its nucleus. Wrapped in a cloud of 2 electrons, the anti-helium they built was its perfect reflection, holding 2 antiprotons and 2 antineutrons, circled by 2 positrons. To make even a handful of those atoms, you need a ring of machinery many meters across. Pushing particles close to the speed of light, you collide them, study the debris, and search for the rare signatures of anti-helium among a blizzard of other fragments. Then you must catch those few atoms without letting them touch anything at all. In that quiet triumph, the team managed to create exactly 9 anti-helium atoms. They lived for only a tiny fraction of a billionth of a second before striking the detector and dissolving into light. Those 9 atoms, invisible to any ordinary eye, confirmed something gentle and profound. Antimatter follows the same laws as matter. The way anti-helium absorbed and emitted light matched the behavior of regular helium. Its structure mirrored the familiar atom perfectly. In principle, nothing forbids the existence of whole anti-stars or even anti-galaxies burning somewhere beyond our horizon. Astronomers listen for them. If large islands of antimatter floated near islands of ordinary matter, the boundaries between the two would shimmer with high-energy gamma rays as particles wandered across and annihilated. Space telescopes scan the sky for that particular pattern. So far, everything visible seems to be made of normal matter. If antimatter realms exist, they either lie far beyond what we can see, or they never formed in great numbers at all. On Earth, the antimatter we do create wears a strange crown. It is, in a sense, the most expensive substance we know. Estimates suggest that a single gram of antihydrogen would cost tens of trillions of dollars to produce. And yet, you cannot truly use it as a fuel in any easy way. The energy you could gain from its annihilation is exactly the energy you had to spend making it, only paid up front in electricity, engineering, and time. Any container, strong and complex enough to hold it safely, would weigh vastly more than the fuel itself. Even so, the dream persists, because matter-antimatter reactions are so efficient. They tempt the imagination of people who think about journeys to the stars. A modest amount of antimatter could, in theory, push a spacecraft to a noticeable fraction of light speed. But the questions that follow are heavy. How do you store something that destroys itself on contact with ordinary matter for years at a time? How do you control that annihilation gently, like a flame you can turn up and down? How do you shield human bodies from the fierce radiation? And how could any civilization afford to make such fuel in the first place? The drama of annihilation is not only a distant idea. When an electron and a positron meet, they spiral together, speeding up until, in an instant, they vanish and are replaced by two gamma-ray photons flying off in exactly opposite directions. Those twin flashes carry a very specific energy, like a signature. Wherever positrons are born and die, that signature appears in the spectrum of light. Even medicine quietly relies on this. In positron emission scans, patients receive tiny amounts of substances that emit positrons as they decay. The positrons drift only a short distance inside the body before meeting electrons and vanishing in pairs of gamma rays. By tracing those rays, doctors build detailed pictures of how different parts of an organ are behaving, revealing hidden tumors or subtle changes without any surgical cut. Far above, in the thin air where cosmic rays crash into molecules, matter and antimatter pairs are created and destroyed endlessly. The showers of particles they spawn fall toward the ground, and without you ever noticing, many pass through your body each second. Earth's magnetic field gathers some of the charged antiparticles born this way, trapping antiprotons in the radiation belts high above the surface, around planets with strong magnetic fields, like Jupiter and Saturn. Similar invisible rings likely exist in carefully designed magnetic traps. Scientists have held single antiprotons for more than a year, the longest any piece of antimatter has ever stayed in human care. The moment the fields switch off or fail, the particles rush outward, touch ordinary matter, and end their story in tiny sparks of energy. If antimatter is rarity born from violence, there is another kind of rarity that whispers instead of roars, scattered through all the rocks. Water and soil of Earth is an element so scarce that, taken together, there may be less than a small spoonful of it in the entire planet. It is element 85 on the periodic table, called astatine, a name drawn from an old word meaning unstable. It is fiber-bide. Unstable hardly captures its nature. Astatine simply does not stay itself for long. The most long-lived version manages only a few hours before its nucleus breaks apart. Many forms survive just seconds. Any astatine that may have been present when Earth was young has long ago decayed into other elements. The tiny amount that exists now appears as part of the slow breakdown of heavier elements like uranium and thorium. For a brief step in their decay chains, an atom becomes astatine, then almost immediately turns into something else. Because it is so fleeting, scientists cannot hope to mine astatine or gather natural samples. By the time you knew an atom had formed in some rock, it would already be gone. To study it, researchers make astatine artificially. In particle accelerators, they bombard bismuth targets with alpha particles, creating astatine nuclei one by one. Even after decades of effort, the total amount of astatine produced by human beings is far less than a millionth of a gram, spread thinly across many experiments. Its restlessness comes from the crowding inside its heart. 85 positively charged protons are squeezed into a space so small that the repulsion between them is enormous. The strong nuclear force is only just enough to hold them together. A tiny quantum tremor is all it takes for the nucleus to fall apart. No one has ever seen a lump of pure astatine with their eyes. From its place below iodine in the halogen family, scientists guess that if you could somehow gather enough of it, astatine might appear as a very dark, perhaps metallic solid. The lighter halogens grow darker as their atoms grow heavier. From almost colorless fluorine to deep, shadowed iodine, astatine should be darker still. But this picture remains a thought only. Any visible speck would be so radioactive that it would heat itself from within, its own decay acting like countless tiny sparks. Even a microgram, a millionth of a gram, could generate enough heat to vaporize itself and harm whatever held it. It has earned the quiet nickname goodbye element for good reason. And yet, even this vanishing, dangerous element may carry a gentle use. Some forms of astatine emit alpha particles, heavy, short-ranged bursts of radiation that can be deadly to cancer cells while sparing much of the healthy tissue nearby. Researchers are studying astatine 211, attaching it to antibodies that seek out tumors. In early trials, the astatine travels straight to the cancer cells and releases its energy there, like a tiny, precisely placed charge. Its half-life of about 8 hours gives doctors enough time to prepare, deliver, and let the treatment unfold before the astatine decays away. Even with all its promise, astatine keeps slipping through human hands. The same restlessness that makes it useful in medicine also makes it almost impossible to handle. Accelerators can only produce tiny traces at a time, and those traces begin to disappear the moment they are born. Hospitals and nuclear facilities have to choreograph their work like a delicate dance, create the atoms, rush them across distance, and guide them into a patient's veins, all within a few quiet hours, before the element simply ceases to be. If you could somehow gather astatine in amounts you could see, the result would be more like a small star than a simple piece of matter. Every single atom holds a crowded heart of 85 protons, barely held together. When that balance snaps, the nucleus spits out particles at tremendous speed, each decay carrying away energy measured in millions of electron volts. In most radioactive materials, these events are spread out over long stretches of time. One atom decays now, another much later, and the heat seeps away gently into its surroundings. Astatine is different. Its atoms live fast and die almost together. Imagine a grain of sand made of astatine, about a milligram in mass. Inside that tiny speck, there would be an unimaginable number of atoms, and nearly all of them would decay within a single day. Physicists have worked out what that would mean. The little grain would pour out roughly the same power as a bright household light bulb, more than 100 watts of heat, focused into a volume smaller than your fingernail. In seconds, the solid would melt, the liquid would boil, the gas would glow, white hot, before tearing itself apart. If you tried to scale up the amount, the problem would grow just as quickly. Twice as much astatine, twice as much heat, 10 times as much, 10 times the power. At some point, no cooling system could keep up. The sample would chase itself into a runaway fever until it vaporized completely. This is why astatine cannot really be studied as a bulk material. The very idea of a beaker full of it is more fantasy than experiment, so chemists have had to become patient and clever. Traditional methods rely on scooping, weighing, dissolving, and recrystallizing visible amounts of matter. With astatine, you work with numbers of atoms so small that a single stray molecule of something else can distort the results. Instead, researchers sprinkle astatine among large amounts of chemically similar elements, such as iodine. The astatine quietly follows the iodine through reactions like a shadow. Sensitive radiation detectors watch where the astatine goes, step by step, revealing its behavior without ever needing a pure lump. Those tracer studies, along with careful theory, paint a curious picture. Astatine behaves like a halogen, and yet not quite like one. It shows hints of metallic character as well. It sits on the border between metals and non-metals, sometimes acting like each. Supercomputer calculations help fill in what experiments cannot reach. Models suggest that solid astatine would form little pairs of atoms, bonded together the way iodine does, and those pairs would pack into a crystal. The bonding appears to be a blend of metallic and covalent character, a kind of hybrid between familiar categories. Laser experiments that probed the energy released when astatine captures an extra electron matched these predictions closely. A small victory in a field where most of the subject vanishes between experiments. And yet, for all this delicacy and danger, doctors need only a whisper of astatine to help a real person. Treatment doses contain only billions of atoms, a number that sounds large but is vanishingly small by the standards of chemistry. These doses are expensive to make, costing tens of thousands of dollars, and they exist in a useful form for only about 8 hours. Nuclear facilities and hospitals must work in careful rhythm, sending and receiving this invisible cargo and guiding it swiftly to the tumors it is meant to harm, before the element decays back into silence. Astatine may be the rarest naturally occurring element we know, but it is not the rarest kind of matter humans have ever coaxed into being. Once you step beyond the top row of the periodic table's natural residence, you enter a region where elements do not simply hide. They do not exist on Earth at all unless created by us. If you were to sit with a periodic table and count the elements from 1 upward, you would find that every number up through 94 appears somewhere in nature except 1. At 61, there is a gap, an empty square. This is promethium, named after the titan who stole fire from the gods. The name fits. Promethium is a kind of fire that never sits still. For a long time, that empty square was a true mystery. Chemists knew something should be there. The neighboring elements, neodymium and samarium, are rare earth metals found in many minerals. It would be reasonable to expect their sibling to appear as well. But no matter how carefully they examined ores and rocks, no matter how refined their separation techniques became, promethium never appeared. Many claimed they had finally found it in the years between the world wars. But each claim dissolved under scrutiny. The signals turned out to belong to other elements or to experimental mistakes. The answer came from a different direction entirely. In the mid-1940s, at a nuclear facility in Oak Ridge, Tennessee, scientists studying the products of uranium in a reactor found what they were looking for. When uranium nuclei absorb neutrons and then split in fission, they create a wide variety of lighter elements. Among that debris, they isolated an unfamiliar substance whose properties matched the missing element exactly. Promethium does not appear in nature in any significant amounts because all its forms are unstable on human timescales. The longest-lived version, Promethium-145, has an average lifetime of only about 18 years. Any promethium born when Earth was young is long gone. Today, promethium appears mainly in two ways: as a rare byproduct of uranium, slowly splitting apart in rocks, and as an artificial product of reactors and particle bombardment. Natural uranium occasionally undergoes spontaneous fission, making traces of promethium that then decay away within years. The total amount of naturally occurring promethium in the entire planet at any moment is estimated to be on the order of a few hundred grams. Human industry has produced less than a kilogram in total, spread over decades. Because it is so scarce and so active, promethium has only a few uses. At one time, its oxide was used in small nuclear batteries for satellites, where the steady decay could be turned into electricity. Its radiation can excite nearby materials so that they emit a soft blue-green glow. For a while, this led to luminous paints for watch dials and instrument panels that required no charging from outside light. In time, safety concerns won out. The health risks to workers handling the paint and to people wearing it against their skin were too great, and those applications faded. Even in chemistry classrooms, promethium is more legend than substance. Students can hold pieces of copper or iodine in their hands, but promethium remains a blank square on a chart, something known mostly from tables and numbers. Researchers who wish to study it must apply for special permits and work in controlled environments. The material arrives in amounts too small to see, sealed behind layers of shielding. Experiments must be designed to work with mere nanograms, billions of times lighter than the coins in your pocket. Some of its compounds, like promethium oxide, have intriguing optical properties and have been considered for exotic lasers. But the cost and difficulty of making enough material have kept those ideas mostly on paper. Far away, in the hearts of stars, promethium is less shy. In certain dying stars, nuclear reactions forge it as part of a chain of heavier elements. It does not last long before turning into samarium, but for a brief moment, it is there. By analyzing the colors in a star's light, astronomers occasionally see the fingerprints of promethium, a sign that intense nuclear processes are at work in those stellar atmospheres. It is a reminder that all the heavy elements we know, from iodine to gold to uranium, were born in stars and stellar explosions. The presence or absence of particular elements on Earth tells a story about the nuclear past that shaped our world. From there, it is a small mental step to an even stranger kind of matter. One that never appears on Earth at all, unless nature has compressed it in the hardest way she knows. Imagine taking a teaspoon and dipping it into the surface of a distant star, then bringing that teaspoon home and putting it on a scale. The needle would not just swing, it would tear through the dial. That spoonful would weigh billions of tons, enough to crush through the scale, through the floor, through Earth's crust, and sink toward the core. This is neutron star matter, where atoms have been pressed beyond recognition. Neutron stars are what remains when very massive stars run out of fuel. With no more energy to hold themselves up, their cores collapse inward under their own gravity. Electrons are forced into protons, forming neutrons. The result is an object no larger than a city, yet containing more mass than our sun. You can imagine compressing all of humanity, billions of people, into a space the size of a sugar cube. Even that image does not quite reach neutron star density. In every cubic inch, there is mass comparable to an entire mountain. At the surface of such a star, gravity pulls with a strength that is almost beyond words. Perhaps 100 billion times stronger than the gravity you feel now. A fall of just a few centimeters would accelerate an object to immense speeds before it struck the crust. Under such pull, mountains can rise only a few millimeters before they slump back down. The outer layer is thought to be a rigid lattice of iron and other nuclei, forming a crust perhaps a mile thick, harder and stronger than any material we could create. Beneath that crust, the world turns liquid and strange. The neutrons there are thought to flow as a superfluid, a quantum liquid with no viscosity, no internal friction. Waves in this sea would not fade as they travel. They could, in principle, slosh back and forth forever. Deeper still, the pressure grows so intense that even neutrons, which themselves are made of 3 quarks, may begin to merge and dissolve. The quarks could form new patterns, creating an exotic quark liquid rather than distinct particles. Theory suggests this transformation might occur when densities reach a few times those found in ordinary atomic nuclei. Conditions likely to exist in the cores of some neutron stars. We cannot cut into a neutron star to see what lies inside, but the universe gives us hints. Some neutron stars send out beams of radiation that sweep across space as they spin, like lighthouses on a cosmic shore. To an observer aligned with those beams, the star appears to flash with remarkable regularity. Some of these pulsars keep time more precisely than our best atomic clocks. By studying their spins, their slowings, and their sudden tiny jumps, physicists infer how rigid or fluid the interior must be. Over the past years, astronomers have also measured neutron stars that are more massive than earlier theories thought possible. Some of the heaviest known examples contain roughly twice the mass of our sun, squeezed into a sphere only a couple of dozen kilometers across. According to many older models, such stars should have collapsed into black holes. Their very existence forces scientists to revise their understanding of how matter behaves under such staggering pressure. It hints that the stuff inside is stiffer than expected, that the strong force binding quarks and nucleons together resists compression with surprising tenacity, perhaps delaying or complicating the transition to quark matter. When 2 neutron stars spiral together and merge, the universe shakes. The collision can melt both stars and fling out jets of neutron-rich material at significant fractions of the speed of light. some of that material becomes the seeds of heavy elements like gold and platinum. The merger may briefly form an even more massive neutron star or collapse swiftly into a black hole. As they dance and collide, these stars send ripples through space-time itself, gravitational waves that we can now detect on Earth. The way those waves rise and fall carries information about the softness or stiffness of neutron star matter. Softer matter compresses more easily and leads to different wave patterns than stiffer matter. So far, the data suggest that neutron star interiors resist compression more strongly than many models predicted. This in turn implies that the strong nuclear force remains intensely powerful, even at densities that approach or exceed those inside ordinary nuclei, and that quarks may hang on to their confinement longer than we once thought. When we stare into the hearts of neutron stars and wonder what lies beyond their crushing densities, the questions become almost dreamlike. What does matter do when it is pushed as far as it can possibly go? Does it simply push back, growing ever stiffer? Does it slip quietly into some new Y, the exotic state? Or does it finally surrender to gravity and fall into a kind of nowhere? A singularity? To follow that thread, we have to look very closely at what matter is made of. Everything familiar to you, from your bones to distant galaxies, is built from two simple kinds of quarks. Called up quarks and down quarks, they always cluster in groups of three. Two up quarks and one down quark make a proton. Two down quarks and one up quark make a neutron. Those protons and neutrons gather into nuclei. Electrons drift around them, and atoms appear. On the surface, it feels wonderfully simple, but nature's menu is richer than that. In total, there are 6 known kinds of quarks. Up and down are only the lightest pair. 4 heavier flavors exist with wonderfully odd names: strange, charm, top, and bottom in everyday matter. These heavier quarks are absent because they are too massive to be comfortable. They appear briefly in powerful collisions and then fade away, turning into lighter quarks almost at once. Strange quarks earned their name because the particles that contained them, when first found, behaved in ways that seemed, to physicists, genuinely strange. They lived longer than expected and decayed in unusual patterns. A strange quark is tens of times heavier than an up or down quark, and in normal conditions, that extra weight makes it unstable. The weak nuclear force quietly rearranges it into lighter quarks in a tiny fraction of a second. Inside particle accelerators, strange quarks are born whenever protons are smashed together with enough energy. They form brief families of particles, then decay, vanishing from the scene almost immediately. For a long time, this made it easy to ignore them when thinking about stars or planets. Yes, strange quarks exist, but only as sparks in the dark, created in laboratories and in rare, energetic cosmic events. They were not expected to shape the bulk matter of the universe. Then a simple question was asked: what if, under crushing pressure, strange quarks become comfortable? What if, in that environment, they stop being fleeting visitors and decide to stay? At first, that sounds backward. Heavier particles are usually harder to keep around. They require more energy, not less. But the quantum world often steps in with its own rules. Quarks belong to a family of particles called fermions. They obey a principle that says no two identical fermions can share the exact same quantum state. That rule forces them to stack up in energy levels like people filling seats in a theater from the bottom row upward. Once the low seats are taken, new arrivals must sit higher up, at higher energy, inside extremely dense matter, such as the core of a neutron star. Almost all the low-energy seats for up and down quarks may already be full. To add more normal quarks, you have to push some of them into very high-energy states. Under those conditions, something surprising can happen. Creating a strange quark in a low-energy seat can cost less total energy than leaving a down quark in a high-energy one. In that cramped quantum crowd, a strange quark can actually be the cheaper option. Calculations suggest that at densities a few times higher than those inside ordinary atomic nuclei, quark matter might rearrange itself into a mixture with comparable numbers of up, down, and strange quarks. This mixture is called strange quark matter. In theory, it might be at least as stable as ordinary nuclear matter, perhaps even more so. If that is true, strange quarks in that environment would no longer hurry to decay. They would settle in and stay, forming a new phase of matter. In this picture, strange quark matter is like a lower resting point on the energy landscape, a substance made from roughly equal parts up, down, and strange quarks could have slightly less energy per particle than the familiar protons and neutrons around us. That would make it a better minimum, a truer ground state. Ordinary matter would then be only metastable, like a ball resting in a shallow hollow when a deeper valley exists nearby but is hard to reach. Computer simulations that try to capture the behavior of many quarks crowded together hint that something like this might be possible. The strong nuclear force, which binds quarks into protons and neutrons, behaves differently when many quarks overlap in a small space. Exotic effects nicknamed color superconductivity may appear, allowing quarks to pair up in delicate patterns, somewhat like electrons in a superconductor. These pairings could lock strange quarks into a stable, crystalline liquid, unbelievably dense and strong. If such matter truly exists, it could form objects that do not need gravity to hold them together. They would be self-bound, kept intact by quark interactions alone. In space, such objects might occupy a narrow mass range between ordinary neutron stars and black holes. Too light, and gravity can never squeeze matter enough to trigger the strange phase. Too heavy, and gravity wins entirely, collapsing everything into a black hole. Somewhere in between, there may be room for strange stars, whole celestial bodies made largely of strange quark matter. We cannot yet say whether any of the compact stars we see are genuine strange stars, but there are hints that some neutron stars behave oddly. A few seem smaller and denser than expected for their mass. Others cool more quickly than standard models can easily explain. These clues may mean their cores have undergone a transition to strange matter, hiding a new phase of the universe deep inside a shell of more ordinary material. The most dramatic possibility arises when we imagine pieces of strange matter not as stars, but as fragments. Theorists call these tiny droplets strangelets. Picture a bead of liquid so dense that a speck no larger than a grain of sand weighs as much as a mountain. Strangelets would be made entirely of quark matter, with up, down, and strange quarks mingling freely. Their size could range from clusters only slightly larger than an atomic nucleus all the way up to macroscopic grains. If strange stars form in the cosmos, violent events like neutron star mergers might tear them apart, flinging out strangelets into space the way foam is cast off by colliding waves. Each fragment would be held together, not by electromagnetic bonds between atoms, but by the direct action of the strong force between quarks. A strangelet the size of a virus, in this picture, could weigh as much as a small mountain. From far away, a strangelet might masquerade as an unusually heavy version of some familiar element, cloaked in a thin shell of electrons that neutralizes its charge. Detecting such objects is very difficult. In transit, they would act like cosmic rays with extremely large mass and relatively low charge, slipping through magnetic fields with only a slight bend. Most detectors are tuned to catch lighter, more strongly deflected particles, and a strangelet could simply pass by unnoticed. Some scientists have even asked whether a strangelet, if it touched ordinary matter, could act like a seed, coaxing nearby nuclei to reconfigure their quarks into the strange arrangement. In that scenario, a chain reaction might unfold. Each newly converted region of strange matter would help convert its neighbors, spreading through normal matter like ink through water. This idea is both captivating and unsettling, and it led to serious safety reviews when powerful colliders such as the Large Hadron Collider were first switched on. The conclusions of those reviews were quietly comforting. Nature has been conducting high-energy collisions for billions of years, in the form of cosmic rays striking Earth's atmosphere with energies that dwarf anything human machines can create. If strangelets that trigger catastrophic conversion were easily made, the Earth and many other planets would have been transformed long ago. Our continued existence is strong evidence that, if strangelets can form at all, they do not behave in this apocalyptic way. Accelerator experiments have searched for signs of strangelets, particles with unusual mass-to-charge ratios and unexpected stability. So far, nothing has been clearly seen. That does not entirely rule them out, but it narrows the possibilities. It may be that strange matter, if it exists, prefers environments with sustained pressure and density, like the cores of neutron stars, rather than the brief flashes of quark soup created in laboratory collisions. This brings us back to the violent embrace of merging neutron stars. When two such objects spiral together and collide, they create conditions unlike anything on Earth. For a few seconds, enormous amounts of matter are held at ultra-high densities and temperatures. Shock waves ripple through this material, and some is flung outwards at great speed. If strange quark matter can form anywhere, these collisions are prime candidates. Gravitational wave observatories have recorded the ripples from several neutron star mergers. In at least one case, the combined mass of the two stars should have overwhelmed ordinary neutron matter, forcing an immediate collapse into a black hole. Instead, the signal suggests a highly compact object lingered for a short time before disappearing. It is tempting to wonder whether such remnants could be strange stars, their inner cores stabilized by strange quark matter. If so, fragments of that material might have been ejected, drifting now between the stars as invisible, incredibly dense droplets. All of this leads to an even deeper question, one that feels almost philosophical. What if strange quark matter is not just a curious possibility, but the true resting state of matter itself? In that case, everything you see and touch would be, in a strict sense, only temporarily stable. A long-lived but not ultimate form. Atoms feel permanent to us, because their lifetimes are far longer than human history. Protons and neutrons cling together extremely well. Electrons seem content in their orbits. We build our trust in reality on that quiet persistence. If strange quark matter sits at a slightly lower energy, it would be like a deeper well at the bottom of a valley. Our current world would be balanced on a ledge, separated from that lower well by a high barrier. To fall in, matter would have to undergo an extensive rearrangement. Nuclei would dissolve. Quarks would unbind and then regroup. Strange quarks would appear in great numbers. Under almost all conditions, the transformation cannot begin. The barrier is just too tall. Introduce a piece of strange matter, however, and the picture changes. The seed shows quarks a different, lower energy pattern they can adopt. Under certain theoretical assumptions, contact between ordinary matter and a sufficiently large strangelet could encourage nearby nuclei to join that pattern, releasing energy as they fall into the deeper well. That energy, in turn, would help convert more matter. In some models, the conversion front could travel nearly at the speed of light. If such a wave started inside a planet, it would sweep through its entire volume in a heartbeat, converting all its nuclei to strange quark matter. The planet's mass would stay the same, but its size would shrink dramatically, perhaps to a sphere only a few hundred meters across, dense and dark, with a surface gravity beyond anything we can easily imagine. From far away, it would still weigh the same. It would simply be an incredibly compact remnant. This scenario sounds like something from a quiet science fiction nightmare, but its reality hangs on very delicate numbers. To know whether strange matter is truly more stable than normal nuclear matter, we must calculate how quarks behave under extreme conditions, using the theory of the strong force, quantum chromodynamics. Unfortunately, that theory becomes very difficult to handle at the relevant energies and densities. The approximations we rely on are still rough. At the moment, the best estimates suggest that strange quark matter might be slightly more stable than nuclear matter, or it might be slightly less. The difference appears to be small, and the uncertainties in our calculations are of the same size as that difference. In other words, our current tools are not yet sharp enough to say for sure. Until theory improves or nature offers a clearer experimental hint, the true stability of strange matter remains an open, softly haunting question. From everything we know so far, most physicists quietly suspect that strange matter is either unstable or only barely stable. 3 simple threads keep pointing in that direction. First, the sky is full of neutron stars. We see them as pulsars, as X-ray sources, as quiet, dense specks orbiting companions. If strange quark matter were much more stable than ordinary neutron matter, we would expect many of those stars to have already converted. Their cores turned strange long ago. Instead, most observations can still be explained with dense but ordinary neutrons. Second, we have been smashing particles together for decades, both in our accelerators and in the natural colliders of the cosmos. Those high-energy impacts are exactly where exotic states might appear. Physicists have searched carefully for long-lived lumps of strange matter with unusual mass and charge, but nothing convincing has emerged. If strange matter were easy to make and easy to keep, it ought to have shown up by now. Third, ordinary matter has simply endured. For almost 14 billion years, atoms have held together in stars, planets, and living things without suddenly dissolving into some deeper state. That long, steady persistence suggests real stability, not a world balanced on the edge of instant transformation. Yet none of these arguments absolutely forbid strange matter. They only tell us it is not common or easily made. Strange quark matter could still hide in the cores of some neutron stars, wrapped in thick shells of neutrons that mask its presence. The brief flashes and accelerators may simply not mimic the sustained pressures inside stars, and the early universe might never have formed strange seeds as it cooled. To truly test strange matter, we would need to recreate neutron star-like densities in a controlled way, and hold them long enough for quark matter to settle into whatever state it prefers. Our machines cannot yet do this. Future facilities might come closer, but they lie far in the future and would cost enormous sums. For now, the most promising laboratory is the sky itself. If strange stars exist, they should behave just differently enough from neutron stars that, with careful watching, we can tell. Their sizes for a given mass might shift slightly. Their cooling patterns could be faster or slower. The way they spin, quake, and swallow matter from a companion could leave subtle imprints in their light. A few compact objects already look suspicious. Some are very small for their mass. Some cool unusually quickly. Some emit radiation that standard models strain to explain. But in each case, more conservative explanations involving complex neutron physics remain possible. One especially powerful clue would be the nature of a star's surface. A neutron star wears a crust of nuclei and a thin atmosphere of atoms. Its X-ray spectrum carries the fingerprints of those atoms, with familiar lines where specific elements absorb and emit. A strange star, by contrast, would have a bare surface of quark matter, covered only by a very thin layer of electrons. There would be no ordinary atoms near the surface at all. The radiation from such an object should have a distinctive, smoother shape, with features that cannot easily be faked by a normal atmosphere. X-ray telescopes have been looking for this kind of spectrum. A few sources have flirted with the strange star interpretation, seeming too small or too hot or too clean in their light. Later observations have often muddied the picture, pulling them back toward the neutron star category. The signals are interesting, but not yet decisive. New instruments with sharper eyes may help us listen more carefully to the surfaces of these stars. Thinking about strange stars leads naturally into even denser territory, where neutrons themselves give way to a sea of quarks. A neutron star already has a nearly unimaginable density. A matchbox of its matter would weigh more than a mountain. In some models, squeeze it further, and the neutrons begin to overlap and lose their individual identity. The quarks inside them melt into a continuous fluid. This is quark matter. Quark matter does not behave like any fluid we know. The quarks are still there as fundamental particles, but their wave patterns overlap so strongly that each one feels the pull of countless neighbors at once. The whole star becomes a single quantum liquid. Flow, viscosity, and pressure all become deeply quantum mechanical. Temperature no longer just means how fast molecules jostle. It connects to how the quark sea itself is excited. Under these conditions, quarks may pair up in special ways, much like electrons do in a superconductor. When that happens, the quark liquid can flow without internal friction, a state called color superconductivity. Theorists have given different possible phases names like color, flavor, locked matter, two-flavor superconductors, and crystalline color phases. each one a different pattern of pairing and symmetry. Which state actually appears depends on the density, the temperature, and which flavors of quark are present, if up, down, and strange quarks all take part in roughly equal numbers. The color-flavor locked phase may emerge, a highly symmetric and stable configuration that some calculations suggest could be the preferred state of very dense quark matter. The transition from neutron matter to quark matter is expected to occur at a critical density, perhaps sharply, like water suddenly freezing, or in a more gradual way with mixed regions where both phases coexist. In those mixed zones, quark matter and neutron matter might arrange themselves into bubbles, layers, or other intricate structures, a kind of nuclear foam deep inside the star. We cannot peel back the layers of a distant star, but we can watch how it behaves. Starquakes, sudden fractures in the crust, can change a pulsar's rotation rate. If a liquid quark core lies beneath, those quakes might send ripples through it, leaving patterns in the star's pulses. Some observed glitches in pulsars hint at a soft, responsive interior. Others can be explained with purely neutron matter. The evidence, as so often in this story, is intriguing but not yet clear. Cooling gives another hint. Newborn neutron stars start out incredibly hot and lose energy over thousands to millions of years, mainly through neutrinos and then through light. Quark matter can radiate neutrinos more efficiently through certain processes than neutron matter can. That would make stars with quark cores cool faster during their earliest ages. Some young neutron stars do appear to cool very rapidly, in line with such models, yet alternative explanations exist. Neutron matter, with additional exotic particles, can also provide fast cooling channels. The heaviest compact stars offer perhaps the strongest indirect nudge. There is a theoretical limit to how massive a pure neutron star can be before gravity forces it to collapse into a black hole. Some observed neutron stars sit uncomfortably close to, or even slightly beyond, the simplest estimates of that limit. When quark matter or strange quark cores are included in the models, the maximum mass a star can sustain increases, making these heavyweight stars easier to explain without invoking immediate collapse. If strange quark matter is indeed more stable at high densities, then a more extreme object becomes possible, a strange star made entirely of strange quark matter from center to surface. It would be only slightly different in size and mass from a neutron star, but its makeup would be utterly different. No crust of nuclei, no atoms, just a dense drop of quark liquid dressed in a thin veil of electrons. In such a star, the density would remain almost constant until very near the surface, then fall abruptly. That sharp boundary affects how light escapes and how the star responds to stress. It also affects the star's landscape. A neutron star's surface is held together mainly by gravity, so even tiny bumps are quickly flattened. Strange matter is held together directly by the strong force as well, giving the surface extra cohesion, in theory, that could allow slightly taller mountains than on a neutron star, not mountains in any familiar sense. Only gentle ridges, a few centimeters high, but enormous by the standards of such extreme objects. As these lumpy stars spin, their tiny asymmetries would send out continuous gravitational waves, faint ripples in space-time. Our current detectors have not yet seen such steady, narrowband signals, which sets limits on how large those mountains can be and how common such stars are. Still, the possibility remains open. Near the surface, strange matter itself may adopt delicate patterns. Instead of atoms forming crystals, clusters of quark matter, little domains of strange quark liquid, could line up in repeating structures. In that thin outer layer, strange matter might freeze into exotic crystalline arrangements, a kind of quark lattice unlike any solid we could ever hold, near the surface of a strange star. The crust itself might be a patchwork of different quark arrangements, like hidden layers of unfamiliar ice, where a neutron star's crust cracks along lines between atomic nuclei. A strange star would fracture between domains of quark matter. The way such a crust rings and flexes, the way starquakes ripple through it, would not quite match the behavior of ordinary neutron star crusts. In principle, very precise timing of pulsars could pick up these differences, letting us tell which stars are strange and which are only extremely dense in the usual way. If two strange stars ever collided, the spectacle would be even more exotic. When two neutron stars merge, they produce a storm of hot neutron matter that may briefly form a heavier neutron star or collapse almost at once into a black hole. If both stars were strange stars, the collision would churn up a sea of scorching, strange quark matter. In that chaos, droplets of strange matter could be flung outward, tiny but incredibly dense fragments that might endure as strangelets and drift through the galaxy for billions of years. Over the long life of a galaxy, if strange stars were at all common, such mergers could seed space with countless strangelets, most of them forever unobserved. A few might wander through our solar system, even through Earth itself, leaving barely a whisper behind. Detecting them would be remarkably hard, like trying to notice a single heavy grain of sand passing quietly through a desert. The search for strange stars continues now in a patient, almost meditative way. X-ray telescopes gain sharper vision, able to tease finer details from the light of compact stars. Gravitational wave observatories listen more sensitively to the chimes of distant mergers. Radio arrays watch pulsars with timing, precision measured in nanoseconds. Each new glimpse helps tighten the net around these possibilities. If we do confirm that strange stars exist, it will be more than a curiosity. It would tell us that quarks can live freely in bulk, outside the prison of protons and neutrons, and that matter has deeper resting places than the ones we experience. But strange stars and quark stars are only one branch of this family of extreme remnants. Some cousins bend physics in a different direction, not by packing matter more tightly, but by twisting space with magnetic fields that almost defy imagination. Earth's magnetic field is gentle enough to feel familiar. It guides compass needles, shields us from some of the sun's charged particles, and at the surface measures on the order of half a Gauss. That seems strong enough for its quiet work. A magnetar takes that same idea and turns the dial up by a factor of about 10,000 trillion. Near its surface, the magnetic field can reach about 1 quadrillion Gauss. Fields that strong do not just yank on compass needles. They reach into the quantum fabric of empty space, at a distance where Earth would orbit. Such a field would erase every magnetic stripe and smart card. Closer in, it could disrupt delicate chemistry and even tug at the shapes of molecules themselves. Only a few dozen confirmed magnetars are known in our galaxy. They are thought to be newborn neutron stars that inherited rapid spins and intense internal motion from their parent stars. As the collapsing core shrinks, magnetic field lines are wound and amplified in a cosmic dynamo, then frozen into the tiny, dense remnant. That stored magnetic energy is immense, rivaling the rotation energy of the star. The field is restless. It wants to relax into a lower energy configuration. When it does, the sudden rearrangement can release a vast amount of energy in a heartbeat. Magnetar flares are among the most violent electromagnetic events we know, matched only by the brightest gamma-ray bursts. In less than a second, a single flare can emit more energy than our sun will radiate over hundreds of thousands of years. In December of 2004, one such flare erupted from a magnetar roughly 50,000 light-years away. Even from that distance, the flash briefly overwhelmed several satellites and noticeably disturbed Earth's upper atmosphere. Had that magnetar been only a few light-years away, the same outburst might have been devastating for life here, close to a magnetar's surface. Physics bends. Light does not quite behave as it does in ordinary space. In fields of that strength, the vacuum becomes birefringent, meaning it treats different polarizations of light differently. Photons split into two modes that travel at slightly different speeds, as though empty space itself had become a strange kind of crystal. Atoms struggle to keep their usual shapes. Electron orbits stretch out along the field lines, turning spherical clouds into elongated cigars. Chemical bonds form and break under different rules. Even the virtual particle pairs that flicker in and out of existence in the vacuum feel the field, aligning briefly before annihilating. Inside the star, magnetic and gravitational forces wrestle. Gravity tries to pull everything inward. The magnetic field pushes sideways, trying to reshape the interior. The crust, already under huge pressure, is pulled and twisted until it accumulates strains far beyond what any earthly material could bear. Eventually, a fracture occurs, a starquake. In that instant, the crust cracks. The field reconfigures, and a storm of energy cascades into accelerated particles and high-energy radiation. A magnetar flare is born. Some magnetars sleep for decades between major outbursts. Others twitch more often, throwing off smaller flares every few years. As they age, their fields gradually weaken, dissipating as electric currents in the crust and core slowly lose energy. Over millions of years, a magnetar can fade into something more like an ordinary pulsar, its tantrums quieting as its internal stresses relax. The interiors of magnetars may be even stranger than their surfaces suggest. Extremely strong magnetic fields can affect the behavior of nuclear and quark matter, shifting the balance between different phases. Some theorists have proposed that in magnetars, the combination of high density and intense magnetism could make it easier for quark matter, even strange quark matter, to appear and remain stable. In that picture, a magnetar is not only a magnetic monster, but also a possible cradle for exotic phases deep within its core. We cannot see inside directly, but we do see consequences. Magnetars spin down, slowing their rotation much faster than typical pulsars, as their magnetic fields extract rotational energy and turn it into radiation. Their X-ray brightness and spectra change over time in ways that hint at shifting magnetic configurations or alterations in the outer layers. Some of them have been linked to unusual bursts of radio waves, possibly connecting magnetar activity to fast radio bursts seen in distant galaxies. Even so, as intense as magnetars are, they still belong to the family tree of stellar remnants, There is another proposed kind of compact object whose roots reach back far earlier, to a time before the first stars ever formed. In the first tiny sliver of cosmic history, the universe was a hot, dense soup without atoms, without galaxies, without even stable nuclei. During this early era, slight variations in density could, under the right conditions, collapse directly into black holes. These are called primordial black holes, because they are thought to have formed not from dying stars, but from the raw initial fluctuations of the universe itself. Quantum jitter during a period of rapid expansion called inflation may have created regions just a little denser than their surroundings. When inflation ended and the cosmos cooled, some of those patches might have crossed the threshold where gravity overcame all other pressures, collapsing into black holes. Depending on exactly when and how they formed, primordial black holes could span a huge range of masses. Some might be as heavy as stars. Others, particularly the earliest and smallest, could have had masses comparable to mountains, or even less, packed into volumes far smaller than an atom. Because they interact only through gravity and perhaps very weakly through other forces, primordial black holes are tempting candidates for some portion of the dark matter, the unseen mass that makes up the bulk of matter in the universe. If many primordial black holes existed with masses between those of asteroids and stars, they would be hard to spot individually. Yet their collective gravity could help hold galaxies together and shape their rotation. Astronomers have looked for their footprints. One method watches for gravitational microlensing, when a compact object passes between us and a distant star. Its gravity bends the light and causes a brief brightening. Large surveys have monitored millions of stars, counting how often such events occur. The rate of microlensing puts limits on how many primordial black holes of a given mass can exist. If they made up all dark matter in certain mass ranges, the sky would show more lensing events than we actually see. Another line of evidence comes from gravitational waves. Some of the first black hole mergers detected by observatories like LIGO involved surprisingly heavy black holes, with masses that are not easily produced by normal stellar evolution in all environments. This led some researchers to wonder if those black holes might be primordial. Others argued they can still be explained as the remnants of very massive stars or stars formed in dense clusters. The ongoing catalog of mergers may eventually reveal patterns that require a primordial contribution, or show that ordinary stellar black holes are enough. There is also a limit from evaporation. According to theoretical work, black holes are not entirely black. They slowly lose mass by emitting radiation, a process called Hawking radiation. The smaller the black hole, the hotter it is and the faster it evaporates. Over the age of the universe, any primordial black hole lighter than a certain threshold would have completely evaporated. That means we cannot find very tiny primordial black holes today. They are gone, leaving only whatever fleeting traces their final outbursts may have produced. Between the lower mass limits set by evaporation and the upper limits from lensing and other observations, there remains only a narrow window where primordial black holes could still hide in significant numbers. Within that window, they might contribute a modest fraction of dark matter, or play special roles as seeds for the growth of supermassive black holes at galaxy centers. The search continues across many fronts: more sensitive micro-lensing surveys, improved gravitational wave detections, gamma-ray observations that could catch the last moments of evaporating black holes. If primordial black holes are real, they would be among the oldest intact structures in the universe. Fossils from the first instance after the Big Bang drifting quietly through space. And unlike the huge black holes born from collapsing stars, the very smallest primordial black holes would face a special fate of their own, a dramatic end that no other black holes share. Imagine a black hole as heavy as a small asteroid, but so compact that its edge, its event horizon, would be smaller than a proton. Its diameter would be about 1 femtometer, roughly the size of an atomic nucleus. Inside that tiny boundary would be more mass than the largest mountains on Earth, crushed into a volume smaller than a single atom. No familiar process in today's universe makes black holes like this. Stars collapsing at the end of their lives form black holes at least a few times the mass of our sun. Only the early universe, in its first furious moments, could have produced such miniature versions. Most of those would have already burned themselves away through Hawking radiation, slowly converting their mass into light and particles until nothing remained. In principle, though, micro-black holes might still appear briefly when energy is squeezed into very small spaces. When extremely energetic particles collide, the energy itself can act like mass. In theories where gravity becomes stronger at tiny distances, perhaps because of hidden extra dimensions, those collisions could create tiny horizons. Some of the highest energy cosmic rays that strike our atmosphere carry enough energy that, on paper, they could form such micro-black holes for an instant. When the Large Hadron Collider was first turned on, a few people wondered whether it might do the same. The idea was not that the Earth would be in danger, the tiniest black holes would evaporate almost immediately, but that we might catch their brief births and deaths in our detectors. If extra dimensions make gravity stronger at small scales, micro-black holes would appear more easily than standard theory predicts, and the collider's proton beams might be just powerful enough. Experiments looked for their fingerprints. A decaying micro-black hole should radiate its mass away as a thermal spray of particles, photons, electrons, quarks, neutrinos, and heavier species, all mixed together in patterns characteristic of Hawking radiation. Detectors sifted through millions upon millions of collisions, searching for those particular showers. None appeared clearly. That silence told us something subtle but important. At the energies we can reach, gravity still behaves just as Einstein described, with no obvious amplification from hidden dimensions. Whatever quantum form gravity takes at its deepest level stays mostly out of sight, waiting for energies far beyond our current reach. If we could create and hold a micro-black hole, its properties would be unlike anything else in physics. Smaller black holes are hotter than bigger ones. Temperature rises as mass drops. A black hole with the mass of a mountain would glow at billions of degrees, radiating fiercely in all directions. It would not just emit light, it would emit almost every kind of particle nature allows, in proportions set by its temperature, like a tiny furnace that cooks everything on the menu at once. The lifetime of such an object depends strongly on its mass. Very small black holes evaporate very quickly, because their high temperature makes them radiate energy away at an enormous rate. Slightly heavier ones live longer, and the relationship is steep. If you double the mass, the evaporation time grows by roughly a factor of 8 near the end, when only a small amount of mass remains. The process accelerates. The black hole gets hotter and hotter as it shrinks, dumping energy faster and faster, until in its final fractions of a second, it releases a burst as powerful as a nuclear explosion. That last flash should appear as a sharp, high-energy burst of gamma rays and other particles. For decades, satellites and ground-based observatories have watched the sky for such sudden events. They have not seen a signature that everyone can agree is an evaporating primordial black hole. That absence tells us that if such black holes exist today, they must be rare, or have masses that finished evaporating long ago. Or Hawking's prediction works differently under real cosmic conditions than we expect. Most physicists still trust the underlying idea. Hawking radiation arises from marrying quantum mechanics with curved space-time, and the reasoning is elegant and robust. Yet, it remains an untested promise. For a long time, all the black holes we could study were too massive and too cold for their Hawking glow to be detectable against the warm fog of the universe's background light. In recent years, though, there has been at least one tantalizing whisper. In 2019, detectors recorded a single neutrino with an energy far beyond the usual, a ghost particle carrying the punch of several protons moving almost at light speed. It had traveled from outside our solar system, arriving without fanfare in the deep ice where the detector waits. When researchers tried to trace back its possible origins, familiar culprits struggled to fit. Ordinary supernovas, active galactic nuclei, and gamma-ray bursts did not quite match the combination of energy and direction. One group suggested something more exotic. Perhaps this neutrino was born in the final instant of a tiny primordial black hole's life, as it completed its long evaporation and exploded in a last fierce pulse of radiation. In such a scenario, a primordial black hole formed in the early universe would spend billions of years quietly losing mass, growing hotter as it shrank, until finally it released its remaining energy in a brief shower of particles, including ultra-high energy neutrinos. The timing, the energy, and the rarity of the event seem to align with that picture. It could be the first indirect glimpse of Hawking radiation from a real black hole. But one lonely event is not enough to settle the story. Other explanations are still on the table. Unusual cosmic ray interactions, or astrophysical engines we do not yet fully understand, might produce similar neutrinos. To move from suggestion to certainty, we would need more examples with the same characteristics. Neutrino observatories around the world now quietly monitor the sky, hoping for another handful of such messengers. Behind these searches lies a deeper motivation. Detecting Hawking radiation would not only confirm that black holes glow, it would connect gravity, quantum mechanics, and thermodynamics in a single, observed phenomenon. It would tell us that horizons are not absolute one-way doors, but gently leak information and energy in a way that reflects the quantum structure of space-time itself. In thought, you can imagine watching a small black hole over its full life in a kind of time-lapse. For most of its existence, almost nothing appears to change. It sits dark and steady, slowly swallowing stray particles and faint background photons, as long as the universe around it is warmer than the black hole itself. It gains more energy than it loses and can even grow. As cosmic time passes, the universe expands and cools. Eventually, for a sufficiently small black hole, a balance point is reached. The background becomes cooler than the black hole's Hawking temperature. From then on, the black hole gives off more energy than it absorbs. Very slowly at first, its mass begins to tick downward. The smaller it gets, the hotter it becomes, and the faster it evaporates. The curve of mass versus time bends gently at first, then more steeply, until near the end it drops almost vertically, ending in a brief, brilliant exhalation. For stellar mass black holes, this entire process takes timescales so long they feel almost meaningless, numbers like 10 raised to the 67th power years, far greater than the current age of the universe. These black holes will outlive stars, galaxies, and perhaps even protons themselves. Only much smaller primordial black holes, with masses closer to mountains or large asteroids, could have completed their evaporation in the present cosmic era. The way black holes radiate carries another puzzle, one that cuts to the core of how we think about information in physics. Hawking radiation is thermal. It depends only on the black hole's mass, spin, and charge, not on what originally fell in. A black hole formed from matter and one formed from antimatter would, in this idealized picture, emit the same fog of particles as they evaporate. A black hole born from collapsing stars and one born in the early universe would look identical at the end. Quantum mechanics insists that information cannot truly be destroyed, only transformed or hidden. Simple Hawking evaporation seems to erase information completely. This clash is known as the black hole information paradox. Either our understanding of quantum mechanics is incomplete in the presence of horizons, or the evaporation process somehow encodes information in subtle correlations between emitted particles, or the entire picture of evaporation needs revision near the smallest scales. At the very end, when the black hole's mass shrinks to a tiny fraction of its original value, our usual equations become uncertain. Quantum gravity, the still mysterious theory that should unite general relativity and quantum mechanics, must take over. And we do not yet know exactly what it will say. Some models suggest that evaporation stops at a smallest possible mass, leaving behind a stable remnant with about the Planck mass, only a few micrograms, packed into a volume smaller than an atom. Others suggest complete evaporation, with no leftover at all. If such remnants exist, they would be almost impossible to find. Each one would be immensely dense yet incredibly small, interacting mainly through gravity and perhaps the faintest of quantum effects. Depending on how many black holes the early universe produced and how their evaporation histories unfolded, these remnants could be sprinkled through space in vast numbers or in none at all. They might quietly contribute to dark matter, or be so rare that their role in the cosmos is negligible. For now, they remain a possibility written at the edge of our equations. Tiny ghosts that could be everywhere or nowhere, waiting for a theory and a telescope sensitive enough to reveal what really happens when a black hole reaches the end of its life. As a tiny black hole fades, it does not only glow with particles and light. Its very grip on space-time changes as the mass slowly slips away. The curvature of space around it softens, and those changes ripple outward as faint gravitational waves. In principle, the pattern of those ripples would carry a record of the black hole's mass and spin as they evolve. One day, more sensitive gravitational wave observatories may be able to hear those whispers from evaporating primordial black holes, especially if they can be linked with matching flashes of light or bursts of particles together. That kind of multi-messenger listening could turn Hawking radiation from a beautiful idea into something seen and measured. The most intense moment, though, comes right at the end. By then, The black hole is no heavier than a small rock. After ages of slow loss, its horizon has shrunk to smaller than an atomic nucleus. Its temperature has risen to unimaginably high values, and radiation pours out furiously. Every heartbeat now removes a noticeable fraction of the remaining mass. The black hole shines across the spectrum all at once: gamma rays, X-rays, ultraviolet light, visible light, infrared, and a storm of particles of many kinds fly away in all directions. Because Hawking radiation strengthens as the black hole shrinks, there is a feedback loop. A smaller mass means a higher temperature. A higher temperature means more radiation. More radiation means faster mass loss, which heats it further still. Eventually, the process runs away. In the last hour, a large portion of what remains is converted to radiation. In the last minute, that fraction grows again. In the last second, almost everything left is dumped into space in a single, brilliant pulse. That final burst would release energy comparable to multiple nuclear weapons in far less than the blink of an eye, with all of it carried by light and particles rather than shock waves in air or rock. Seen from a suitable distance with the right instruments, it would appear as a brief, extremely energetic flash of gamma rays with a very specific spectrum, a thermal curve corresponding to a wildly high temperature, fading over a characteristic timescale that depends on the black hole's starting mass. Smaller black holes would end their lives faster. Slightly larger ones would stretch the finale out a little longer. Alongside the gamma rays would come a burst of neutrinos across a huge range of energies. Unlike light, which can scatter, bounce, and be absorbed by gas and dust, neutrinos hardly notice matter at all. They slip from the dying black hole and travel almost straight outward, passing through stars, clouds, and planets as if they were fog. Catching them would give us a clear line back to the explosion. The final temperatures are so high that for an instant, the black hole can radiate even the heaviest known particles, massive quarks, heavy bosons, perhaps even Higgs particles, all briefly appearing before decaying away. In a sense, each terminal burst would be a miniature particle physics experiment, operating at energies beyond any collider we could ever build. The violence of that last moment should also ring space-time itself. As the mass distribution collapses toward nothing, the surrounding geometry changes rapidly, creating high-frequency gravitational waves. These would be faint and challenging to detect, but they carry yet another piece of the story. For decades, astronomers have searched for these final screams of evaporating primordial black holes. Gamma-ray satellites watch the whole sky, cataloging countless flashes from lightning, solar flares, magnetar outbursts, distant supernovas, and gamma-ray bursts. Somewhere within that busy sky, a terminal Hawking burst might be hiding. The difficulty is to pick out the one pattern that truly belongs to a dying black hole. The absence of a clear detection so far suggests that, if such black holes exist in the relevant mass range, they must be rare, or their bursts must be fainter and more directional than we first imagined. Distance complicates things. A nearby evaporation would be overwhelmingly bright and unmistakable. A faraway one might be barely visible, blending into the background. If the emission is not perfectly spherical, but beamed in certain directions, we would only see the rare cases where one of those beams happens to point toward Earth. Some models even imagine that near the very end, quantum fluctuations could make the black hole stutter, losing mass in small jumps rather than smoothly, producing several smaller outbursts before the final flash. Finding even a single confirmed terminal burst would be a treasure. Its spectrum and timing would test our descriptions of quantum gravity. Its neutrinos would show whether Hawking radiation really behaves like a thermal bath of all possible particles. Its gravitational waves, if we could detect them, would tell us how space-time itself responds in those last instants. Because neutrinos interact so weakly, they play a special role in this search. A neutrino could cross a light year of solid lead and still have a good chance of passing through untouched. Trillions flow through your body every second without leaving a trace. Yet, when a huge number are created at once, a tiny fraction will occasionally collide with atoms in a detector, producing faint flashes of light. Observatories like IceCube in Antarctica, which uses a cubic kilometer of clear ice as a target, watch for those flashes with thousands of buried sensors. From the pattern of light, they can reconstruct where the neutrino came from and how much energy it carried. The very high-energy neutrino reported in 2019, whose energy and direction hinted at something unusual, is exactly the sort of messenger that could come from a black hole finishing its life. Other explanations are possible, but the fact that this one event fits so neatly into evaporation models has inspired a more focused hunt. When a new ultra-energetic neutrino appears, researchers check whether any gamma-ray burst or other bright event occurred in the same part of the sky at the same time. The dream is to catch a paired flash, an intense, short gamma ray burst together with matching neutrinos, both pointing back to a small region of the sky, to sort rare signals from constant noise. Scientists use increasingly sophisticated tools, including machine learning systems trained on simulated data. These algorithms learn to recognize the subtle shapes in the timing and energies of events that a terminal burst would produce, and flag real observations that look similar for closer human inspection. If we ever confirm such a detection beyond doubt, the implications will reach far beyond black holes themselves. The detailed pattern of neutrino energies and flavors would encode information about the very last stages of evaporation, where quantum gravity rules. Different candidate theories about the small-scale structure of space-time predict slightly different terminal behavior. Comparing their predictions to real data would be one of the most direct tests of ideas such as string theory or loop quantum gravity, performed not in a collider hall, but in the quiet depths of a neutrino detector. In the same breath, evaporating primordial black holes tie into another mystery that has been with us for decades: the nature of dark matter. Galaxies spin too fast for the visible mass alone to hold them together. Clusters of galaxies bend light more strongly than their luminous contents account for. Cosmic structure on large scales grows as though there is more gravity present than the matter we can see can provide. We call that hidden mass dark matter. And by most estimates, there is about 5 times as much of it as there is ordinary matter. Many ideas for dark matter invoke new particles beyond those in the current standard model of particle physics. But there is also a quieter possibility. Perhaps some portion of dark matter consists of black holes, formed in the early universe, too small and too dim to see except through their gravity. Primordial black holes would pull on stars and gas exactly the way dark matter does. They would not shine, and they would have formed early enough to help seed the first structures. The trouble is that we do not have a free hand. observations constrain how many such black holes can exist at different masses. Microlensing surveys, which look for the brief brightening of stars as compact objects pass in front of them, have ruled out primordial black holes as the main form of dark matter over a wide band of masses similar to those of ordinary stars. Evaporation and gamma-ray limits exclude very tiny ones. Gravitational wave observations of black hole mergers help constrain others. There remains, however, a window. Black holes with masses somewhere between that of large asteroids and roughly the mass of Earth, or up to a small fraction of our Sun, are hard to exclude completely. They are too heavy to have evaporated yet, too light to produce frequent, easily detectable microlensing events, and subtle enough in their gravitational influences that current surveys may not see them clearly. Within this window, a population of primordial black holes could, in principle, quietly provide a significant share of the universe's dark matter without obviously contradicting what we have measured so far. To probe this possibility, astronomers study the motions of stars in the outskirts of galaxies, watch the fragile structures of ultra-faint dwarf galaxies for signs of disruption, and plan ever more sensitive lensing and gravitational wave experiments. Very light primordial black holes, with masses closer to asteroids than to stars, remain particularly elusive. They slip past most of our tests, neither brightening stars frequently enough to give themselves away, nor colliding often enough to ring our gravitational wave detectors. For now, they remain a kind of cosmic rumor written into the equations, tiny, ancient black holes wandering through the dark, each one a relic of the universe's first heartbeat, and together, perhaps adding up to much of the mass we cannot see hiding in plain sight, without yet breaking a single observational rule. If light primordial black holes do make up some of the dark matter, they cannot be too numerous, even though they are small. Each one would emit Hawking radiation together. Millions or billions of them scattered through a galaxy would create a soft fog of high-energy light, a diffuse gamma-ray glow that telescopes can measure. The fact that we do not see too much of this glow already places upper limits on how many such black holes can exist, and those limits grow tighter as gamma-ray detectors become more sensitive. Some versions of the idea imagine that primordial black holes did not form alone, but in families. Tiny, overdense regions in the early universe might have collapsed into clusters rather than single holes. Those clusters would behave like knots of dark matter, extended halos instead of solitary points. Within each cluster, black holes would orbit and tug on one another, their gravity weaving complicated patterns. Computer simulations that replace some or all dark matter with primordial black holes show a mixed picture. In some ways, galaxy formation proceeds beautifully, with black holes seeding early structure and helping galaxies grow. In other ways, the small-scale details do not match what we see. The masses and distributions of galaxies can come out slightly wrong. These mismatches could mean that primordial black holes cannot account for all the dark matter, or they might point to imperfections in the simulations themselves, which must make many assumptions about the messy physics of gas, stars, and feedback. A more modest possibility is that the universe is mixed. Perhaps most of the dark matter is some unknown kind of particle, and a smaller fraction is made of primordial black holes. In such a blended picture, particle searches would be difficult, because some of the missing mass would hide in compact objects rather than in smooth particle halos. Meanwhile, other observations whisper hints in different directions. Some ultra-high energy cosmic rays seem to arrive from nowhere in particular, their paths pointing toward empty regions of sky rather than obvious astrophysical engines. Some gamma-ray signals near the center of our galaxy look odd, not fitting comfortably with standard dark matter annihilation or known source models. The early universe, as seen by the James Webb Space Telescope, appears to have produced surprisingly massive galaxies sooner than expected, as though something helped them grow quickly from the start. In each case, primordial black holes could play a role, accelerating particles near their horizons, shining faintly across the halo, or providing massive seeds for young galaxies. None of these clues is decisive, but together they suggest that the full story of dark matter and structure formation may be more intricate than a single neat answer. While that puzzle simmers, another mystery waits in the rain of particles that constantly falls on our planet. Cosmic rays are charged fragments, mostly protons and heavier nuclei, that strike Earth's atmosphere from all directions. Most are modest in energy, but a few are astonishing. The very highest energy events carry as much energy in a single proton as a thrown ball, squeezed into something smaller than an atomic nucleus. Known astrophysical accelerators struggle to reach such extremes. Supernova shocks, active galactic nuclei, and gamma-ray bursts all come close. But each has difficulties explaining both the energies and the observed arrival patterns. Primordial black hole explosions offer a tantalizing alternative. As a small black hole approaches the end of its life, its temperature climbs to such heights that the emitted particles can take on extraordinary energies. The final instant of evaporation could send out protons, nuclei, and photons with energies matching those of the rarest cosmic rays we see. If enough primordial black holes in the right mass range were scattered through our galaxy, their collective outbursts over time could account for the observed sprinkling of ultra-high energy events. The chemical fingerprint of these cosmic rays offers one test. Particles accelerated by more ordinary engines are expected to be mostly protons, with some mix of heavier nuclei. A terminal Hawking burst, by contrast, should begin by producing all allowed particle types, more or less democratically. As those particles propagate through interstellar space, magnetic fields and collisions will alter that mix, but subtle differences may remain. Observatories that watch the cascades of secondary particles in the atmosphere can infer, from the shapes of the showers, whether an incoming cosmic ray was more proton-like or more nucleus-like. The highest energy events show a puzzling variety, not fitting cleanly into a single simple source model. Evaporating black holes could naturally produce such diversity, as each explosion happens at a different place, time, and environment. Another clue lies in where these particles seem to come from. You might expect that if they were born near powerful, persistent sources like active galaxies, their arrival directions would cluster along those lines of sight. Instead, the directions of the most energetic cosmic rays are surprisingly scattered, with no strong preference for the galactic center or any known cosmological landmark. At first glance, this randomness looks like confusion, but if the sources are tiny black holes sprinkled throughout the galaxy's dark halo, exploding here and there, it is exactly what you would expect, a pattern that, on the sky, looks almost like noise. Magnetic fields weave through the galaxy and bend charged particles, even at the highest energies. So retracing their paths is never perfect. Still, When researchers fold in realistic models of those fields, some of the observed events could plausibly have come from explosions within a few thousand light years, close enough for the particles to reach us without losing too much energy along the way. Ground arrays such as the telescope array in Utah and the Pierre Auger Observatory in Argentina watch for these rare arrivals, catching, on average, only about one of the very highest energy particles per square kilometer per century. In recent years, a handful of especially extreme events have sharpened the question. One cosmic ray detected in Utah in the early 2020s carried an energy beyond even previous record holders, challenging standard acceleration models. A nearby primordial black hole finishing its evaporation could, in principle, produce such an outlier. The probabilities are delicate. Such events should be rare, but not impossibly so. If a modest population of suitable black holes exists, as more data accumulate, patterns, if any, will emerge. While these invisible black seeds haunt the outskirts of galaxies and the edges of theory, another class of exotic objects might hide in plain sight as stars that are not quite stars. Neutron stars, which we have lived with in our models for decades, wear a crust of atomic nuclei pressed into rigid lattices atop a sea of nuclear matter. Strange stars, if they are real, would be different down to the surface. Their interiors would be made of strange quark matter, and their outermost layers would not contain atoms at all. Instead, at the boundary between the quark liquid within and the vacuum outside, the matter might organize into small lumps of strange quark matter known as strangelets. Surface tension, electric forces, and gravity would conspire to arrange these strangelets in complicated ways. In some models, they hover just above the underlying quark sea, separated by thin layers, forming a kind of foamy or crystalline structure. Each strangelet would carry its own cloud of electrons, and together they might pack into orderly patterns like atoms in a solid crystal, but born from quark clusters rather than familiar nuclei. Such a crust would be very thin compared to the size of the star, perhaps only a few meters deep on a sphere a dozen kilometers across, but its properties would profoundly influence how the star looks and behaves. Beneath it, dense quark matter would extend all the way to the center. Above it, a delicate veil of electrons, only tens of meters thick, would smooth the transition to empty space. Photons climbing out from the surface would have to pass through this unusual boundary, and some energies would be absorbed more strongly than others, leaving subtle imprints in the X-ray spectrum. With sufficiently sensitive telescopes, these spectral quirks might be distinguishable from those produced by a neutron star atmosphere. The way such a crust cracks and shifts would also differ. On a neutron star, starquakes fracture a lattice of nuclei. On a strange star, they would rearrange strangelet domains. The timing and size of sudden jumps in rotation rate pulsar glitches might follow different patterns. Magnetic fields might anchor differently, pinned more or less strongly by the strange crust compared to a nuclear one. Over long times, that could change how quickly a star's magnetic field decays and how its pulses evolve. Some theorists have suggested that under the right conditions, the crust of a strange star could become unstable. As the star slowly gathers extra matter from a companion or the interstellar medium, the added weight might push the crust past a critical point. Suddenly, large portions could collapse inward, dumping material onto the bare quark surface below. The energy released in that moment could accelerate electrons into the magnetic field and produce an intense, coherent flash of radio waves, a fast radio burst, lasting only milliseconds, but visible across vast distances. Many observed fast radio bursts share properties that fit such a picture reasonably well: brief, bright, sometimes repeating, with energies and timescales that match models of crust failures on strange stars. Magnetar flares offer an alternative explanation, and current data can accommodate both ideas. Distinguishing between them will require more precise statistics, polarization measurements, and perhaps catching a burst in multiple wavelengths at once. As observations slowly improve, hints accumulate. Some compact objects cool faster than expected. Some show glitch behavior that feels unusual. A few display X-ray spectra that refuse to fit simple neutron star atmospheres. Each anomaly could be a finger pointing towards strange quark matter just beneath the surface, or each could be another facet of rich, but still ordinary neutron star physics. To be sure, we will likely need several independent signs, all pointing in the same direction: timing, cooling, spectra, and perhaps bursts that together say, softly but firmly, that a quark surface is really there. While telescopes stretch toward finer detail, theorists refine their own maps. Computer simulations now follow millions of strangelets interacting under various conditions, trying to predict how crusts form, crack, and glow. These models tell observers where to look, which frequencies of light, which timing patterns, which classes of objects are most likely to reveal the difference between a nuclear skin and a quark one. And all the while, beneath these crusts and horizons, the rules of the very small and the very curved press against each other, stand at least in thought on the edge of a black hole's event horizon. And ordinary intuition fails. There, quantum fluctuations constantly pull pairs of virtual particles from the vacuum. There, the energy density of empty space flickers and shifts. There, even the smoothness of space-time itself becomes uncertain. At that border, where gravity is strongest and quantum rules are strictest, physics steps into territory we have never truly explored. A place where reality feels both delicate and profoundly strange. That strange border we were approaching, the event horizon, is, in some ways, quieter than its reputation. In the language of general relativity, it is just a smooth surface in space-time, a place where the escape speed happens to reach the speed of light. Someone falling through, with no prior knowledge, would feel no sudden jolt as they crossed. Locally, nothing dramatic announces the line. But as soon as you bring quantum rules into the picture, that surface becomes anything but ordinary. Quantum field theory tells us that even the calmest vacuum is never truly empty. Everywhere, all the time, tiny pairs of particle and antiparticle flicker into existence, borrow a little energy from uncertainty, and then annihilate again. Most of the time, this restless dance leaves no trace at all, near a horizon, though some of those pairs are born right on the edge. If they appear close enough, gravity can tear them apart before they reunite. One partner falls inward, carried past the horizon. The other slips outward and escapes as a real particle. To a distant observer, it looks as though the black hole itself is gently glowing. This is Hawking radiation, emerging not from the interior, but from quantum fluctuations in the curved space-time around the horizon. It feels like a magic trick that should break the rules. The escaping particle carries positive energy. Where did that energy come from if nothing can get out? The bookkeeping is subtle. From the perspective of the horizon, the particle that falls in can be thought of as carrying negative energy, so that the black hole's total mass decreases slightly. Energy is conserved overall, but pieces are counted differently by observers inside and outside. At these edges, energy becomes a relative story, not an absolute one. Describing all of this properly demands the full machinery of quantum field theory in curved spacetime, quantum mechanics laid over general relativity. Even for a simple, non-rotating, uncharged black hole, the calculations are demanding. When you add spin or electric charge, the geometry of the horizon changes. Extra layers can appear, and space-time near the hole begins to swirl. In a spinning black hole, the fabric of space is dragged around with the rotation. Virtual particles born there feel that twist, and the pattern of outgoing radiation becomes slightly directional, favoring some regions over others. If the black hole carries electric charge, charged particles feel both gravity and electromagnetic forces, nudging the radiation spectrum into a different shape. On top of that, the horizon itself is not perfectly rigid in the quantum view. It is more like a statistical surface, defined by probabilities. Quantum uncertainty makes its exact position jitter by amounts so tiny that, for a stellar black hole, the fluctuations are much smaller than the size of an atomic nucleus. For a microscopic black hole, the jitter could be comparable to the horizon's own size. Some researchers have wondered whether delicate patterns in this trembling might carry information about what has fallen in, leaking it back out, encoded in subtle correlations within the Hawking radiation. Quantum mechanics also allows for the possibility of tunneling, particles appearing in regions that are classically forbidden. A particle inside the horizon might, in principle, tunnel outward, joining the stream of Hawking radiation without having enough classical energy to escape. Meanwhile, pairs of particles on opposite sides of the horizon can remain entangled, linked by quantum correlations, even though no signal can pass between them at light speed. Measuring one influences the joint state, raising deep questions about how information and causality work in the presence of horizons. All of this has led to heated debates. One speculative idea, known as the firewall hypothesis, suggests that the horizon might actually be a searing wall of high-energy quanta, destroying anything that falls in. It is an attempt to rescue information conservation, but it clashes sharply with the smooth, gentle crossing predicted by general relativity. The fact that serious physicists can argue for both pictures shows how incomplete our understanding still is. At the horizon, quantum mechanics and general relativity are both essential, yet neither alone tells the full story. We are missing a unified theory of quantum gravity. Different candidate frameworks offer different pictures. In string theory, the basic objects are not point-like particles, but tiny vibrating strings and extended brains applied to black holes. It suggests that what looks like a smooth horizon from afar actually has an enormous number of microscopic degrees of freedom, a kind of quantum texture that could store information. In loop quantum gravity, space-time itself is quantized, built from discrete loops and chunks rather than a smooth continuum. In that approach, The horizon is made of a huge collection of quantum geometric states, each contributing a tiny patch of area. Both viewpoints predict tiny corrections to Hawking radiation, almost invisible for large black holes, but potentially dramatic when a black hole's mass shrinks to the Planck scale. There is also the holographic way of looking at things, born from the idea that all the information contained in a region of space might be encoded on its boundary. A black hole horizon is a natural candidate for such a boundary. In this picture, everything that ever falls in is, in some sense, written onto the horizon's quantum state, and the physics inside is dual to a theory living on the surface. If this is right, then understanding the quantum structure of horizons is not just a niche problem, it touches the deepest questions about how space, time, and information are woven together, turning these beautifully intricate theories into tested science. Though is difficult in a very down-to-earth way, the signals we are chasing are incredibly faint and easily lost in background noise. We are trying to notice the softest whisper in a room full of other conversations. Take antimatter. Creating it in accelerators and trapping it with magnetic fields for brief periods is an astonishing achievement. But at least there we control the environment. Searching for natural antimatter drifting through space is another matter. Many antiparticles behave almost identically to their normal twins in detectors. To tell them apart, instruments on satellites and space stations must watch how charged particles curve in magnetic fields. Positrons and electrons bend in opposite directions. Antiprotons and protons leave mirrored tracks. But cosmic rays contain a whole zoo of particle types. Backgrounds are high. Misidentifications are easy. Only years of data and careful statistics slowly reveal a small excess of true antiparticles over the background clutter. For astatine, the fleeting element that appears near the bottom of the periodic table, the challenge is different. Its atoms decay so quickly that no natural macroscopic samples remain. In laboratories, researchers create single atoms or tiny clusters by bombarding targets with heavy ions. The timing must be exquisite. Instruments must be ready the moment an atom exists, because within hours, or often seconds, it will be gone. To build up a picture of its behavior, scientists repeat the process over and over, gathering faint hints from many individual decays and building an understanding statistically. Strange quark matter, if it exists, is even more elusive. No confirmed sample has ever been seen. Experiments look for unusual tracks in cosmic rays, or anomalies in heavy ion collisions, particles that have much more mass than expected for a given electric charge. Such a signature would stand out against the patterns formed by ordinary nuclei. Yet despite decades of searching, no clear example has emerged. The universe may simply not make strange matter in appreciable amounts, or it may make it in ways our detectors are not tuned to recognize. A null result does not easily tell us which primordial black holes, by their nature, hide well. They do not shine unless they are very small and near the ends of their lives. They make no sound. Their gravity is subtle unless you pass very close. Gravitational microlensing provides one of the few direct ways we have to glimpse them. When any compact object passes between us and a distant star, its gravity bends the light and brightens the star for a short period. By monitoring millions of stars, astronomers can catch these events and infer the masses of the lenses. Planets, brown dwarfs, stellar remnants, and black holes all produce such signals. To pick out primordial black holes from this crowd, we have to read the detailed shape and timescale of each brightening, like reading a fingerprint from a brief flicker. Even somewhat more talkative objects, like magnetars, can be tricky. They do emit flares and afterglows, but we must catch them in the act. Measuring their magnetic fields is indirect, relying on models of how their spin slows, how their X-ray spectra behave, and how their bursts unfold over time. Hawking radiation, in the gentle version from stellar black holes, is so weak that the glow is completely buried beneath the cosmic microwave background. The only realistic chance we have of seeing it directly is to catch the final, violent breaths of evaporating primordial black holes. But those final flashes must be distinguished from many other explosive cosmic events: gamma-ray bursts from dying stars, flares from magnetars, collisions between neutron stars and black holes. We rely on multi-messenger observations, light, neutrinos, gravitational waves to cross-check each candidate and discard most of them, inching toward the rare event that fits only the evaporation picture. As instruments grow larger, more sensitive, and more finely tuned, phenomena that were once only theoretical possibilities begin to swim into view. Each new generation of telescopes and detectors opens a little more of the dark. Yet there are also limits written into the laws themselves. Some things are not just currently invisible, they are forbidden. In atomic nuclei, for example, there is only so far you can push the periodic table. As you add more and more protons, their electric repulsion grows stronger. The strong nuclear force holds them together. But beyond a point, the balance tips and the nucleus becomes violently unstable. Theorists predict a small island of stability around certain combinations of protons and neutrons. Atomic numbers near 114 are often mentioned, where lifetimes may be longer than average. But even there, the respite is only temporary. Atoms significantly heavier than uranium cannot last beyond brief instants. They flare into existence and then fly apart. Neutron stars face a similar kind of limit in a different guise. Pack too much mass into such a star, and no known pressure can hold back gravity. Neutron matter reaches its breaking point. Even the stiffest proposed quark matter phases strain and give way, above roughly 3 times the mass of our Sun. Any compact remnant must continue collapsing until a black hole forms. Exotic matter can push the boundary a little, but not remove it. And even black holes themselves are not entirely free of boundaries. There is a smallest, meaningful scale in nature, set by the combination of fundamental constants that define the Planck length and Planck mass. A black hole with a mass around a few tens of micrograms would have a horizon only a tiny bit larger than that fundamental length. At or below this scale, our classical picture of space-time as a smooth surface with a neat, well-defined horizon simply breaks down. Whatever a black hole becomes there, it is no longer the simple dark sphere drawn by general relativity, but something governed by the full, unknown rules of quantum gravity. A final reminder that even the universe's most extreme objects live within limits, and that beyond those limits, we are still only guessing in the dark. There is a smallest black hole we can meaningfully talk about. A place where mass, length, and time all shrink toward the Planck scale, and our familiar picture of a smooth horizon stops making sense. Whether anything smaller can exist depends on the full theory of quantum gravity we do not yet have. The rules that would tell us how space and time behave when they are no longer continuous, but grainy and uncertain. At the opposite extreme, there is also a ceiling. A black hole cannot reasonably be more massive than the part of the universe we can see. A hole that heavy would wrap its horizon around everything, leaving nothing outside to observe it from. The very idea becomes self-contradictory. In a quiet way, the fact that we see galaxies instead of a single, all-swallowing horizon tells us that black hole masses are bounded from above by observable reality itself. Temperature has its own bookends. On the low side lies absolute zero, the point where motion in matter reaches its minimum. On the high side, there is the Planck temperature, around 10 raised to the 32nd power degrees, where thermal agitation would be so fierce that space-time itself would boil. At those energies, quantum gravity would dominate, and the word temperature would lose its usual meaning. Between those extremes, the cosmos gives us stars and nebulae, cold dust and warm planets, each living comfortably in a narrow band where physics stays gentle enough to make structure. Density behaves in a similar way. Everyday solids sit far below nuclear density. Neutron stars climb close to that limit. Quark stars, if they exist, might press a little beyond, but there is a point at which gravity simply cannot be resisted by any possible arrangement of matter. Beyond that, collapse becomes inevitable, and a horizon forms. Stable matter can be very dense, but not infinitely so. Even information knows when to stop. According to the Bekenstein bound, there is a maximum amount of information that can be stored in a given region, and it grows not with the volume, but with the area of the boundary. A black hole reaches this limit exactly. It is the most efficient information storage device nature allows per unit area. In this way, thermodynamics, quantum mechanics, and gravity are tied together in a single quiet sentence about how much detail reality can hold. These boundaries are not engineering problems to be solved someday by clever beings. They are woven into the fabric of the laws themselves. No species, however advanced, can build a device colder than absolute zero, or create a stable object denser than what gravity will allow, or squeeze more bits into a surface than a black hole does. Some speculative particles would run headlong into these limits. Faster than light tachyons would twist cause and effect into knots. Certain imagined magnetic monopoles and particles with imaginary mass would wreck conservation laws or destabilize the vacuum. On paper, they might look intriguing. In the full light of consistency, they simply cannot be. And yet, quantum mechanics leaves a little softness at the edges. It allows particles to tunnel through barriers they classically should never cross. It lets energy be borrowed for brief moments under the umbrella of uncertainty. Black holes that classical physics would treat as eternal eventually evaporate if we trust Hawking's arguments. Things that seem forbidden in the everyday sense sometimes do happen with probabilities so small we can barely write them down. For the rarest phenomena, this distinction between forbidden and merely very, very unlikely matters. If the chance is truly zero, no amount of space and time will help. But if the chance is even the tiniest non-zero number, then, in a universe as broad and old as ours, somewhere, sometime, it should happen. That is how antimatter, once a strange prediction in an equation, became a real thing we can trap. It is why we consider strange quark matter seriously inside neutron stars. It is why primordial black holes and evaporating horizons remain on the table, not inevitable, but permitted. True impossibilities are different. They would break the logical bones of the laws themselves, create paradoxes that cannot be resolved. A perpetual motion machine that spins forever while doing useful work without any fuel is not just impractical, it contradicts the basic bookkeeping of energy. No clever design will save it. Distinguishing which ideas fall into which category allowed, but rare, or fundamentally impossible, is one of the quiet tasks beneath the drama of discovery. Observations help, but they do not speak in absolutes. When we search for something and fail to find it, we can tighten the bounds on how common it might be, but we cannot prove it absent in every corner. The lack of detected strangelets in cosmic rays may mean they are truly scarce, or that they hide in forms we have not anticipated. The missing flashes of evaporating primordial black holes tell us such events, if they happen, are uncommon. They do not yet tell us they never occur. Sometimes it is the combinations that are the most elusive. Each extreme phenomenon we have talked about: strange quark stars, primordial black holes, magnetar fields, antimatter streams might be individually allowed, but imagine stacking them together. A star made entirely of strange quark matter, with a magnetar strength magnetic field, having captured a knot of primordial black holes in its core, its surface gently spitting out both matter and antimatter. Nothing in our current understanding outright forbids such an object, yet the path to making it would require a whole chain of cosmic accidents, each with a tiny probability. When you multiply all those little chances together, the likelihood of that particular combination appearing anywhere within our own galaxy becomes vanishingly small, even expanding your view to the entire observable universe, with its trillions of galaxies and uncountable stars. The odds feel slim. Maybe somewhere a single such chimera exists. Briefly, maybe not. Our instruments are sensitive only within a modest neighborhood, a few thousand light years, where individual stars and remnants can be studied in detail. Beyond that, the strangest children of physics, if they exist, blur into anonymous points of light. Yet within that modest neighborhood, we have already stumbled upon objects that earlier generations would have found unbelievable. Magnetars were only recognized in the last few decades. Candidates for strange stars arise from careful fits to unexpected cooling curves and X-ray spectra. Ultra-high energy cosmic rays crack into our atmosphere, carrying more energy than any human-built accelerator. Each time we extend our reach or sharpen our tools, the universe admits to another surprise. The rarest natural object may well lie in a regime we have not yet entered, perhaps in the first slivers of a second after the Big Bang, perhaps deep inside horizons, perhaps in quantum fluctuations of space-time itself. It might flash into being only under conditions that have occurred once, or a handful of times, in all of cosmic history. It might leave signals we do not yet know how to read. Antimatter galaxies, if any exist, would be that kind of rarity. Vast islands where antimatter won the early coin toss instead of matter, kept apart from us by distances so large and boundaries so violent that mixing would light up the sky with gamma rays. Stable strangelets drifting on Earth, delivered by ancient cosmic rays and now sunk toward the core, would be another. Tiny grains of exotic matter, hidden forever, out of reach. A primordial black hole smaller than an atom, gliding silently through the solar system, would be a third. detectable only through the faintest tug on orbits if it passed very close. Each of these possibilities is linked to the others by the underlying laws. Antimatter points to symmetry breaking in the early universe. Astatine and other fragile nuclei tell us where the strong force yields to electric repulsion. Strange quark matter probes how quarks behave when crowded. Primordial black holes connect quantum mechanics and gravity, and Hawking radiation ties those to thermodynamics. Together, they form a delicate web, showing that nature does not just allow extremes, it seems to seek them out, filling the spectrum from the very lightest to the very heaviest, the coldest to the hottest, the rarest to the almost common. There is a quiet pattern in all of this. Wherever the laws leave a door ajar, the universe eventually wanders through. If neutron stars can exist, then somewhere one will form with the maximum possible mass. If cosmic rays can be accelerated to a given energy, at some point, one proton will ride that highest wave. If microscopic black holes can evaporate, at some moment, one will reach its final, bright whisper. Given time and space enough, whatever is not strictly forbidden tends to show up. And then there is us. We are not outside this pattern, the specific arrangement of atoms that makes up your body. Your brain, the small part of you listening to these words, is unimaginably unlikely when measured against all the ways matter could have been arranged. The chain of events that led from the first stars to heavy elements, to planets, to life, to minds able to wonder about strange stars and Hawking radiation, is a long string of improbabilities. Yet here you are, resting in the dark, letting thoughts drift across the rarest corners of physics. So what is truly the rarest thing? You could choose antimatter in bulk, or astatine atoms, or strange quark matter, or primordial black holes finishing their long evaporation. You could point to consciousness itself, a fleeting pattern of electrical whispers in a brain, reflecting on the universe that made it. Or you could step back and say that perhaps the rarest thing is this particular universe, with these particular laws and constants, capable of making all of these wonders at once. From a physicist's point of view, rarity might mean an event that is almost never realized. But when it is, reshapes how we understand everything from a gentler, more personal view. Rarity might be what you are feeling now, the simple wonder that there is anything at all, that the night exists, that distant stars burn, that you have the time and quiet to think about them. We have wandered together from trapped anti-helium atoms underground to limits at the edge of space-time. We have floated past quark stars and magnetars, listened for death whispers of tiny black holes, and traced the outlines of the boundaries that all things must respect. Along the way, the universe has shown itself to be both strict and wildly creative, obeying firm rules while spinning out endless variations. Maybe, in the end, the rarest thing is the way those rules can give rise to meaning, to curiosity, to stories, to this shared, sleepy journey through the dark. Thank you for drifting through it with me. Somewhere out there, the rarest things continue to unfold in silence. For tonight, it is enough simply to know they are possible, and to rest inside that quiet, improbable truth